Hi everyone. So we'll be continuing off where we left off last time with section 1.2 about divisibility. So let's see what's going on here. So we apply the division algorithm and we can always divide numbers up and get a remainder as a quotient as well as a quotient. And we're interested in the case where we have the remainder being 0, and we would like to understand the factors from a deeper way than elementary school. So let's do that. Let me grab just a little bit of water. So, divisibility. So we have the following definition. That A and B be integers is B not equal to 0. We say that A or B divides A if you can repeat B a certain amount of times to reach A. If A is B times C for some integer C. So in symbols, we write B divides A. So let's do some analysis. So we have the following remark. If B divides A, then that means you can repeat B certain amounts of time to reach to A. For some C belonging to the integers. Then if you multiply both by -1, then you get negative A is B times negative C for some integer minus C belonging to Z. So that means that if you have B divides A, then it divides minus A. So therefore, you can also have the analogous statement. So analogously, if B divides minus A, then by the same argument, we have that B divides A. So what this say is the following remark, that A and negative A have the same divisors. So let's do a couple of more analysis about the divisors of A. So first of all, the reason I said you repeat B certain amount of times to reach to A is because of the following statement. So if B divides A, then that means if we repeat B a certain amount of times, we reach A. So that tells you that, in particular, we have that the absolute value of A is the absolute value of B times C. So then from this condition, we have that 0 is less than or equal to the absolute value of B, which is less than or equal to the absolute value of A. Because you've repeated B, C amount, or the absolute value of B, C amount of times, which is a positive number, to reach A, so it cannot really be bigger than A. It must be less than or equal to A. So what this tells you is that if you do some algebra, then this tells you that B is bound between negative absolute value of A and positive absolute value of B, where A and B are randomly chosen integers, where B is a factor of A. So this tells you that B is bound between negative absolute value of A and positive absolute value of A. So what this tells you is that every divisor that is non-zero that divides A must be less than or equal to the absolute value of A, and an integer has only finitely many divisors. So that's the first point into the prime factorization theorem, which tells you that any integer can be factorized into products of prime uniquely up to perturbation. So we get the following remark. The first thing is that a non-zero integer has only finitely many divisors. And the second thing is that those divisors can only reach a certain bound. So every divisor of non-zero integer A is less than or equal to the absolute value of A. So we can attach certain number to two numbers being the greatest common divisors of two numbers. So first of all, given any number, you can always find that the number itself divides itself. So if you have any number such as A being an integer, then we can see that A divides A because A times 1 is A, and also 1 divides A because 1 times A is A. So that means that any two numbers have as common divisor 1 all the time. So you can attach a number or a way to connect two numbers together by the concept of the greatest common divisor by asking yourself, I want the greatest factor that divides both numbers. And that would be, it cannot reach by what I've said. It cannot be like it is well defined because there's only finitely many divisors of two numbers, and it cannot go down forever because one is a divisor that is positive and divides both numbers. So first, let's write that definition down. So, definition. Let A and B be integers, not both 0. The greatest common divisor GCD of A and B is the largest integer D that divides both A and B. In other words, D is the GCD of A and B, provided that we have the following. First of all, that D divides A and D divides B, first thing. And the second thing is if C divides both A and B, then you must have that C is less than the greatest divisor of A and B, less than or equal to. So the greatest common divisor of A and B is written as GCD of A and B, or just bracket A and B, or HCF of A and B. So that's common notation for it. So notice here that the GCD between any two numbers, but what I've said earlier, is bigger or equal to 1, because 1 is always a divisor of both numbers, or of any number. So we'll use this idea. But first, let me discuss the following result, which is Bezout's theorem. So let's say we get the highest common divisor of A and B. Then I'll tell you an intuition about Bezout's theorem, which we will touch on next time. I'll touch on it in extreme detail. But let me tell you my intuition about it. So tell you that given two integers, the greatest common divisor of both integers can be written as a linear combination of both. So what is the intuition here is that if you have two integers and you take linear combination of both, then you're moving with respect to both, though you're moving certain amount of steps with respect to both integers. So in particular, it will reach the movements of the integer which goes as a factor of both integers. And it will capture all the movements, all the linear combination of both integers if like that integer, that factor will capture all the linear combination of all movements if it is the greatest common factor. So I'll discuss that intuition more next time, but just to give you like a little bit time to think about it, because in my opinion, if someone reasons their way through an intuition, then they will be able to form a deeper intuition with respect to themselves. All right. Thank you, everyone, and I'll see you in the next video.